Welcome to this class on bimolecular reactions. So today we're going to talk about two theories. The first one is collision theory, or CT, and the second one is transition state theory. TST. Okay, both can be used for gas phase and solution situations, which have different precisions, but basically people were looking for a way, if we look at a bimolecular reaction, let's say A plus B gives a product with a second order reaction rate constant K2, is can we predict this K2? Yeah, that was a central question. And collision theory was the first one to be developed. And this was around 1916 to 1918 by Max Troutz and William Lewis. And transition state theory followed after in about 1935 by the people that we've already seen in the introduction chapter: Evans, Eyring, Polanyi, and Wigner, and others. Okay, so if you think about the reaction between two compounds, right? So maybe questions to you. What do you think is important? So the probability for a reaction, let's say first for the gas phase, to occur depends on what? Just take a moment to think about this. Gas phase, so things flying around, bumping into each other. So probably it has something to do, so this means scales with. So it probably scales with the speed, the average speed, right, of the reactants. Probably the number or the density of the reactants. And what else? What can you think of? The size of the reactants. Right? So these three together basically determine the frequency of collisions. So let's look at it a bit more graphically. So if we have A plus B gives product P, and let's say this is a molecule, and we have a certain radius of A and a certain radius of B, right? So the size. So of course this product will be larger, right? And if we look at, how much larger would that be, we don't really know, but what is important is to know what's called the reaction cross-section. So if we imagine A and B to be in contact, right? So this is A, this is B. And we look at their centers, we can look at this distance. And that distance, D, is of course simply the radius of A plus the radius of B. And so the cross section, let's do it in a different color, is basically a sphere, or a disk in this case, where reaction is likely going to happen, right? And so this green area has, so the reaction cross section, sigma AB, will be pi times d squared. Okay, so from the kinetic theory of gases, we know that a molecule say A, that is moving, has a mean velocity C dash, so dash means mean, which is 8 times Boltzmann constant times temperature over pi times ma to the power half, where ma is the mass of the molecule A. Okay. Oops, sorry. There we go. So the molecule will sweep a volume in a certain time, which is sigma AB, right? Reaction cross section times the mean velocity. So if you look at the units, so meter squared times meter per second, so that will be meter cubed per second. Okay, so now for a certain reaction, for reaction AB, so we have a two-body problem, as they call it. We can use something called reduced mass. This is quite simple. Mu AB is mass A times mass B over mass A plus mass B. And then this mean relative velocity, so relative between AB, will become 8 kBt over pi mu AB to the power half. Okay, so let's now come to the collision frequency. frequency, which is ZAB is NA times NB times sigma AB times this thing, right? BT over pi mu AB to the power half, where this is the number density. So it has units 1 over cubic meter. So it's the number of molecules of A per cubic meter. The cross section was in square meters, right? And then let's look at the other units. So Boltzmann is joule per Kelvin. Temperature would be in Kelvin. This is just a number, pi. And reduced mass has units of kilogram. Okay, so if we want to express that in SI units, we have 10 to the 6th times Avogadro squared times concentration A times B times the same term over pi times mu AB to the power half. Okay, so there we go. So there are a number of other aspects that we have to consider. One is that not all the collisions lead to a reaction, right? So the velocities must cross a threshold which is of the Arrhenius type, which is e to the power an energy over RT. In addition, not all the orientations lead to a reaction. So you can imagine if you have a Diels-Alder reaction, the reactants have to be in a pre-organized state to give the product, and that will not happen for all orientations. So there is a steric factor, which is called P, which accounts for all these aspects. Okay. So the final result of that is that the reaction rate of a bimolecular reaction, gas phase, so let me write it, bimolecular gas phase reaction, the rate is the rate constant times Na times Nb, which will be ZAB times the steric factor P times exponent minus E activation over RT. Okay, let's move on to transition state theory. Okay, so there are two postulates. One, so A plus B will form a species that undergoes a simultaneous reaction either to the product or back to the reactants. Second, you assume there is a transition state. So we say A plus B is in a pre-equilibrium with the transition state, which will indicate like this, and then undergoes a reaction with this transition state rate constant to the product P. So this state here, sorry, the transition state, which is an unstable species. So its concentration is negligible. Right, so graphically, this will be like you're used to, right? So if we look at an energy landscape, we have something like this. A plus B, here's the product, here's the transition state. Okay, so we can write a equilibrium constant, which is the concentration of transition state over that of A times B. If we look at the rate of product formation, dP dt, it will be K transition state times the concentration of transition state, which will be K transition times K big K transition times A times B. Okay, so the change in Gibbs energy delta G naught is minus R times T times ln K. Okay, so that is the Gibbs energy of activation. Okay, and that is delta G naught, which will be delta G of the transition state minus, sorry, not delta, of course, G of the transition state, the energy of the transition state, minus that of the reactants. Just clean this up. Okay, so we're talking about bimolecular reactions. So we're considering second order rate constant. K2 of the reaction. So K2, I told you at the beginning of the class, that's kind of the goal of these theories, is to predict this second order rate constant. Will be this, which is K transition state times exponent of minus delta G naught transition state over RT. And since we know G equals H minus T times S, right? We can rewrite that. K2 is K transition times exponent delta S of the transition state over R times the exponent minus delta H of the transition state over R times T. Okay, so later we will look at this. Define K. Okay. So let's look at the representation of the transition state with potential energy surfaces. Why? For the determination of K transition state. Okay, so let's imagine we have a reaction, which is a radical reaction, plus P gives R plus X P. So it's a radical transfer. Okay, so let's look a bit closer at this transition state. So it would be Rx plus P radical would be in pre-equilibrium with a transition state, which then reacts to the final products. So here we have a distance Rx and we have a distance Rpx. Okay, so let's try to construct this surface potential. Okay, I skipped ahead a bit to make this wonderful drawing. So if we look at the reaction states, let's say we are here in state, let's call it alpha. Here we're at the transition state, and here we're at state gamma, right? So if we would extract this profile in this potential energy surface, so this is, again, this is a low region. Low is blue, and then it goes green, more green, it goes up, and then here it goes even higher, up more. Just try to imagine this as a three-dimensional plot. So if we extract the reaction profile, right, then here we are again like this, where it will be alpha, beta, gamma. Sorry, this is reversed, right? So we are first starting, of course, with this distance Rx, the shortest. All right, so we start gamma, then transition state alpha. Okay. So the transition state is at a saddle point. Right, so if you look in this region, so this is of intermediate height, the two sides here going more up, and towards the reactants and the products down. So it has a saddle shape. Okay, so this is potential energy. Okay, so imagine X is sliding from gamma to alpha, right? So X is what we are transferring. So we go from R to P, and X is moving along. So from the kinetic theory, which we saw a bit before, its mean velocity of X, right? So V mean is kb times t over 2 pi m. And now this is the effective mass of the transition state. Okay, that's the kind of hypothetical concept. And we have a certain distance from R to, at some point, what we call the transition state, which this distance, we'll call it delta. Okay, so the rate of passing through the transition state is V average over delta. So we can define a rate constant V over delta times QT transition state, and this is the what's called translational partition coefficient, which comes from statistical mechanics. Okay, so we'll get back later to that one. So we can rewrite that as kbt over 2 pi m of the transition state times 1 over delta times 2 pi m transition state times kbt to the half, what I have here, over Planck constant times delta. And basically you can already see, right, that this term and this term, sorry, not the whole term, but this part and this part will drop out. Delta versus delta will drop out. So we are left with kbt over Planck, right? So Planck constant. That's now actually fixed in relationship to the kilogram since a couple of years, which is 6.62 10 to the minus 34 kilogram times meter squared per second. Okay, again, there are some deviations. and those are captured in kappa, which can go from 0 to 1. And so this is called the transmission coefficient. Okay, so let's combine all of that. So for a bimolecular molecular rate constant in transition state theory, we have kappa times Boltzmann over temperature times temperature over Planck times exponent minus delta G of the transition state over R times T. So this is a very nice result, but there's always a but, right? So, transition state theory is also called the theory of absolute reaction rates. So a priori, before I start, I can tell you the reaction rate, but it only works for the gas phase, which is of course a huge limitation. Neither the reactant, neither of the two reactants is electrically charged. So the theory breaks down if they are charged. And the potential energy change along the reaction coordinate. Is concave downwards. So, like we saw before, it is of the familiar form like this, with this the transition state. Okay, so as a reminder, for a second order reaction, we said that K2 was, kappa times K Boltzmann times temperature over Planck times this equilibrium constant of the transition state. And we can express an equilibrium constant in terms of molecular partition functions and delta epsilon 0, which is the difference between the lowest energy levels of the species. Okay, so let's see what that looks like. So we have the equilibrium constant of the transition state, which will be Q0 over QRX0 times Q0P exponent delta epsilon 0 over KB times D. So just on these molecular partition functions, because probably you're not very well up to speed with those things. So general info. Okay, so in general, molecular partition functions enable us to calculate the probability of finding a collection of molecules with a given energy in the system. Okay, so the probability of a system having energy EI is probability EI is exponent minus EI over KB T over Q and Q. So these are these weird things we were using before, is the sum of exponent minus beta times EI, which this is a Boltzmann factor. And beta is 1 over KB T. So energies in general in a system, EI, can consist of different contributions. So you have electronic contributions to energy, vibrational, translational, and other. Let's just separate that a bit. Okay, let's finish this info section here. So for simple systems, transition state theory works. Like if we have this reaction, gas phase, right? So the proton is just transferred from one to the other, but not for even slightly more difficult reaction. So overall, still the theory is quite limited. Don't worry, I won't expect you to reproduce this last part as long as you have a basic understanding of what is transition state theory and the main concepts.